I think we should get started. So welcome everybody to the 7th MIT International Colloquia on Thermal Innovations, or otherwise known as InnoTherm. We're really excited to have you all here today. And the topic of this panel discussion will be focused on extracting water from air, where we have these really esteemed researchers in different areas that are going to talk about their perspectives and then open it up to Q&A. I first want to introduce our moderator for this session, who is Professor Zhang. I believe this is actually the hardest job in these sessions. And he is currently an associate professor in the Department of Mechanical Engineering at Khalifa University of Science Technology in Abu Dhabi, UAE. And his areas of expertise are broad in the areas of phase change heat transfer, microfluidic flows, 3D printing, and nanofabrication, as well as concentrated solar power generation and cooling, and multi-phase flows for subsurface flows and water treatment. So please join me in welcoming Professor Zhang to moderate this session.
Thank you, Evelyn. Okay, let me just share my slide. Okay, today we are going to have mainly a few speakers here. So the first one is Professor Zhang, and Zhang is a professor of international health from Johns Hopkins, and also she was a director of institute for in Zimbabwe, and also her research area mainly on intervention to prevent child undernutrition in low middle income countries, and also environmental enteric dysfunction. Also the role of sanitation and hygiene on child stunting. So next speaker will be Professor Guihua from UT Austin, and he is associate professor of material science and mechanical engineering. And also he got multiple awards. For example, he's also a fellow of the Royal Society of Chemistry and the Institute of Physics. And his research area mainly on nanomaterials for energy science and environment, and energy storage and conversion, and water treatment and water harvesting technologies. So next speaker, we're going to have Professor Peng Wang from, he has joined appointment with King Abdullah University of Science Technology from Saudi Arabia, and also from Hong Kong Polytechnic University. And he has been with KAUST since 2009. He got multiple awards, and also his research area mainly on clean water production, and also atmospheric water harvesting, and also he is well known in environmental nanotechnology. And our last speaker is Professor Ruzhu Wang from China and the Shanghai Jiao University. And Professor Wang is the university chair professor and the director of Institute of Refrigeration and Cryogenics, and also director of Engineering Research Center of Solar Energy of the Ministry of Education in China. And also definitely Professor Wang is very well known in China. He got many awards like a National Research Award, and also National Teaching Award, and multiple awards from international society like Japanese Heat Transfer Society, and also International Institute of Refrigeration. And his major interest is heating and cooling and thermal management. Okay. So I also would like to remind all our participants. So today we are going to have presentations from panelists, about 40 minutes. Then after that, we are going to have a panel discussion. And in between, we are going to have 2 polls. I just want to remind you. And also, if we really encourage you to submit your questions from right here, this here you have this, you can see my later here. This is a Q&A right here. See, if you see this button, you just click and put your question there, and then our student assistant is going to select question, and I'm going to just put a few questions here just to share with our panelists, and we can discuss, okay, interactively. Okay, I just want to remind you also this seminar and the curriculum is recorded, okay, will be posted on YouTube, and also we are going to we may not able to address all the questions, and many questions we are going to also post it to share with the community. Okay, so if you want to be anonymous, then we can also, you don't need to put your name over there. Okay, it's fine. Okay. So with that, we're going to start the first presentation from Professor Jing. Okay, Jing, please. Thank you very much.
Thank you all so much. It's such a pleasure to be here. And my job is not to talk about atmospheric water harvesting, but to underscore the huge global consequences of poor water access and the urgency of developing innovation engineering solutions to improve water access for people around the world. Children throughout the world grow taller at a remarkably similar rate between birth and 5 years of age, regardless of race, culture, diet, or geography, if they are free of disease, have nutritious food and health care, and live in a clean environment. This has allowed the World Health Organization to develop reference norms of height for age for use in all countries in the world. Now, of course, tall parents have tall children, but that genetic influence doesn't really kick in until after 5 years of age. Children whose growth is constrained by impoverished living conditions are short for their age. These little boys are all 4 years old. The red line is the WHO median height for 4-year-old boys, and the blue line is 2 standard deviations below that median. Children with a height more than 2 standard deviations below the standard, like these 3 little boys on the left, are defined as stunted. Stunting develops between conception and 2 years of age. Children in Asia and Africa, who are in the green and orange lines here, are born about a half a standard deviation below normal length for age, and then fall further and further from normal until about 2 years of age, when the median child in these populations is 1.5 to 2 standard deviations below normal. After 2, there is little to no catch-up. The damage has been done and is largely irreversible. These first 2 years of life are also the period of rapid growth of many other systems of the body, including the brain. 23% of the world's children are stunted, making it the most common form of malnutrition. And we don't really mind that children are short, but what we mind are the other consequences. Children who are stunted at 2 are more likely to die in early childhood, to attend fewer years of school and perform more poorly while they are there, and to earn less money as adults. So we care about stunting because it is an indicator of lifelong human capital. For many years, we have known that the structure and the function of the lining of the small intestine is very different for people in industrialized compared to impoverished living conditions. Oops. For people who live in countries like this European city on the top, the lining of their small intestine has these long finger-like projections called villi, which create miles and miles of surface area for nutrient absorption. But for people who live in impoverished situations like this village in Africa at the bottom, the gut wall is flat and inflamed. This disorder is called environmental enteropathy or environmental enteric dysfunction, and is primarily caused by environmental exposure to fecal contamination. And we have hypothesized that it underlies stunting. We hypothesized that if we could implement an intense water, sanitation, and hygiene, or WASH intervention, we would reduce fecal exposure, environmental enteric dysfunction, and stunting. 3 randomized controlled trials were conducted in Zimbabwe, Bangladesh, and Kenya to test this hypothesis. I was the PI of the Zimbabwe site. These were multi-million-dollar investments, primarily by the Gates Foundation, and they were the first ever randomized controlled trials of sanitation on human health, involving more than 19,000 pregnant women and their children. We tested the water, sanitation, and hygiene interventions that have been commonly available and recommended for low-income rural areas for decades, that include the improved latrine, point of use water chlorination with water guard or another chlorination substance, hand washing stations that are not connected to a water source in most cases with plenty of soap. And we, in these studies, delivered these commodities to the doorstep of the household of the participating families, along with intensive education to motivate hygiene behaviors. The results of these 3 trials were published in 2018 and 19. And in all 3 trials, we found that the wash intervention had absolutely no effect on stunting. Moreover, nearly all the laboratory studies of stool specimens showed that children who received these wash interventions were already infected with at least one pathogen by the time they were a month old. And the average child was already infected with 3 of these pathogens by his first birthday. And there was no difference in the infection rates between children who received the wash intervention and those who did not, showing that this intensive wash interventions with currently available interventions for rural areas of developing countries had virtually no impact on reducing fecal exposure. These 3 trials and other studies have shifted 3 paradigms in our thinking about wash and health. Virtually all kids are persistently infected with pathogens originating from fecal contamination from an early age. This continuous infection is the main driver of poor growth and cognitive development, causing huge losses in human capital of entire populations. And the low-cost wash interventions that governments, UN agencies, and non-governmental organizations have been recommending and implementing for decades do not prevent these infections, even when they are intensively implemented with millions of dollars from the Gates Foundation. These have resulted in consensus and interpretation papers published over the last year, which all basically call for transformative wash, a radical change in wash services available to poor people. And central to transformative wash is meeting the aspirational goal of the UN Sustainable Development Goal for Water, SDG 6. SDG 6 calls for universal provision of water that is free of infectious pathogens and toxins, provided in sufficient quantity for domestic needs at an affordable price, and available on plot. The minimum required volume for domestic requirements is 20 to 50 liters per capita per day. This is the volume needed not just for drinking and cooking or consumption, but also hygiene. Having sufficient water is even more important, Having sufficient water quantity is even more important for human health than achieving a very high level of quality. And that is because water quantity available, water access, determines the amount of water used for hygiene. Access to water must be affordable, and we estimate that it should be that whatever technology is developed should be less than the cost of digging a borehole, or we could consider that it should be no more than about 25% of the total income of an average African family, which is about $600 a year. So if you can calculate out what we're looking for is a technology that could provide water at about 2 cents per liter. And that means that the family would have to spend 25% of their total income on water. I think that of all of the parts of the SDG 6, the part that is most challenging is that we want to have access to water on plot. That is, providing water on the yard or in the household of every household in the world. And this graph shows why. This is the per capita of water volume used as a function of the return time to collect water. And what you'll see is a sharp decline from about 50 liters per capita used when the water's available on plot to only 15 to 20 liters when the source is just 2.5 minutes or about a 5-minute return trip away from the house. So even having the pipe stand in the center of the village vastly reduces the amount of water that's used for hygiene. I first read about atmospheric water harvesting just as our results were coming out and connected with Professor Wang, and we convened a meeting with senior global WASH engineers to discuss whether atmospheric water harvesting could contribute to achieving SDG 6, and published this brief report of our meeting in March in Lancet Planetary Health. We identified these characteristics of atmospheric water harvesting that make it attractive for people in rural areas of low and middle income countries. First, of course, it provides a high quality of water. But most importantly to me is that it decentralizes water access to point of use, off the grid, and can be built to be completely powered by solar energy. On-plot water will improve gender equity, a major global goal, because it is mostly women and girls who spend 200 million hours a year carrying water. These are the minimum specifications that the group defined for a new technology, that it would need to produce at least 500 to 200 liters a day at a cost of about 2 cents per liter, and that it must be culturally acceptable. We talked about this quite a bit, and we would encourage engineers to consult with and talk with end users and engage them in the development of such a technology. So I'll stop there and turn this over to the engineers.
Thank you very much, Jean. I think this is really exciting. Thank you for sharing those slides. And those, I think you like from the health point of view, you basically impose those kind of requirement, also formulate the problem for very well for our engineers and the scientists. And also today we have a few other speakers from materials, from device, also from process system point of view. We're going to share our kind of solutions or recommendations on this topic. Okay, so that will be, I think this will be very exciting. Okay, also at the end we can have some discussion afterwards. So before that, I would like to launch a poll. Okay, just want to our participants to share also your opinion about. Let me see where's the poll here. Okay, so the first poll I'm going to launch just for all the participants to vote. Okay, you can see the questions. Okay. So how much water do you think we have in the atmosphere? Please vote, okay? We'll give you a few, 1 or 2 minutes to vote. It's very interesting to see the number. So number is coming, okay. Wow, okay, very good. I think we have, we collect a lot of votes. Okay, almost there, okay. Okay, very good, coming, okay. So, yeah, almost 80%. Please put your vote as soon as possible, okay? We're going to launch the results soon. Okay, good. So I think we're ready to go, right? Let's just end the polling. Okay. So I want to share the results with you. So we have actually, how many people voted? Okay, for the 10% of all water in river on Earth, only 10. Okay, 26% people vote that. Okay, and also 6 times all the water in river and on Earth. Okay, so basically this is we get the 35% people vote. Okay, so the water in atmosphere is about 6 times all the water in river and on Earth. Okay, so this is very kind of promising, right? That's why we should have this kind of seminar today. So very good. Okay, we will have more discussion afterwards. Okay, good. Now we leave the floor to second speaker, Professor Guihua Yu from University of Texas at Austin. Guihua, it's your floor. Guihua, you can start now.
Okay.
Yeah.
So first of all, many thanks to Evelyn and then Gang for kind invitation, and also other InnoTherm organizing committee members for organizing these stimulating webinar series. And then following the Jean's great motivational presentation on critical needs of freshwater generation. So I will now focus more on the material aspect for atmosphere water harvesting technologies. So currently over 3 billion people worldwide suffer water shortage. And although the various water purification technology exists from the reverse osmosis to thermal desalination, but they typically depend on the natural water resources and mainly feasible in coastal areas, and it typically involve high capital costs and significant infrastructure and energy requirements. And atmosphere water is actually very ubiquitous and present regardless of geological or hydrological conditions. So extracting the water from air is a promising method to provide portable, family and community access, off-grid access to the safe, drinkable water, especially for developing countries. And then currently, there are 3 main methods for atmosphere water harvesting. So fog harvesting, dewing, and moisture capturing. And so for fog harvesting, typically use large meshes or nets to capture the small water droplets suspended in the air, and the dewings refrigerate the air below the dew point to the condensed water vapor. So both for fog harvesting and the dewing have geographical and climate restrictions. But in contrast, the moisture harvesting is very promising and for like a wider applicability because moisture is everywhere on the earth. So I'm going to focus on this sorption-based moisture harvesting today. So let's start with the mechanism first. So the sorption-based moisture harvesting typically involve 2 steps. One is this water vapors being taken up by the sorbents, either through the adsorptions or absorptions. And the second stage is desorption. So the sorbent will be isolated from the ambient and the heat is applied to the sorbents to release the water vapor and then condense to liquid. So adsorption is actually more the molecules to stick to the surfaces of your absorbent, either through the physical or chemical absorptions. But in contrast, absorption is actually the incorporation of water molecule into the bulk volume of your absorption. For example, for water harvesting with hygroscopic materials. So they involve these hydration reactions. And for absorption, so they require the material to have a high surface area to be able to serve as an absorption sites. The second step of desorption really requires heat, a lot of energy involved. So to overcome this absorption enthalpy and to reach the regeneration temperature and to sufficiently lower the relative humidity in the material to release vapor from the absorbent. So if you look at like the traditional desiccants for these moisture harvesting, so they are like silica gels, zeolites, or hygroscopic salts. So silica gel is one of the most commonly used material for moisture capturing. So they have this polar hydroxy group as the sorption center to form the hydrogen bonds with the water molecular. And the zeolite is another widely used solid for moisture harvesting. So they have this 3D network composed of silica and then alumina that contain alkali metals too. So the aluminum metal is the sorption size that has the coordination with the water molecular. And then the polar structures of the zeolite will determine the water harvesting capacity. However, these two commonly used materials have the limited capacity. So generally around 0.3 to 0.5 kilogram water per kilogram of absorbent. And then the high water affinity also make this water release process very difficult, so require a lot of energy. And the hygroscopic materials such as lithium chloride or calcium chloride or the liquids in the liquid sorbents can harvest the water by these hydration reactions, and then can actually have high water uptake even at low relative humidity. But they have the problem of particle agglomeration during the hydration, and the level which will reduce the permeability of water vapor and then decrease the absorption capability. And the morphs are actually a novel class of materials. So they are crystalline porous, composed of metal containing inorganic building centers and organic ligands. Through this coordination bonds into the 3D interconnected networks. So they are highly porous, highly tunable, can provide numerous sorption sites, and by tailoring their structures and composition, so relevant properties such as hydrophilicity, pore size, and volume can be tuned for desired sorption and desorption behaviors. But generally, there's a general limitation for these materials is this desorption process requires significant energy for water release. So if you look at this one example, this slide shows one of the first morph-based water harvesting devices by Omayagi from Berkeley and Abdullah from MIT. So you can see here this water absorption isotones for this zirconium-based morph A01. So at least at a temperature about 25, they have these rapid and stepwise increases for the water absorption capacity with very relatively small relative humidities. And the morph A01, so for this different temperature, 25 and 65. So you can see if a temperature swings between 25 and 65, so it's about quarter of a liter water per kilogram of morph that can actually be generated. And they demonstrated a very promising prototype devices. So this is a device picture showing showing the morph layers, condensers, and also with the heat sink. To the right is these the droplet growth information as the function of time, and also the, as a function of temperature for this morph layers. So this actual device is completely passive, only requires the sunlight as low-grade heat to dissolve and then to condense the collected water. And the bottom right actually shows there's some representative temperatures for these different layers as the function time of day. So in an optimized condition, so this device is capable of harvesting about 2.8 liter of the water per kilogram of morph daily at a relative humidity around 20%. So it's a very promising step in the field. And another class of materials actually is composites. So this is typically involving hygroscopic salts incorporated into the porous solid matrix. So this is to avoid these particle aggregations for better cycling stability, for better yield. So this slide showcase several examples. So first example is hollow carbon spheres incorporating lithium chloride from Peng Wang's group's work, and then through the hard template method. So you have this hygroscopic lithium chloride as the core, and then you have these porous hollow carbon shell as the photothermal layers. So they can enable this multi-cycles every day for the efficient water capture and release. And the lithium chloride as a hygroscopic materials, so they can also be incorporated into morph materials. So this is case using chromium-based morph. So they can provide large contact areas and also a suitable pore diameter for nanoscale crystallization of lithium chloride. So this is also a promising design incorporating the lithium chloride into the morph. And the last example is this ternary design. So you have this polyacrylate as the hydrogel with good chemical stability and water retaining ability. And then you have a carbon nanotube as a photothermal to generate heat, and the calcium chloride is actually used as hygroscopic to take in the water vapor from ambient airs. But generally, as I mentioned early on, so there's one big challenge is this desorption process requires a lot of energy. But if you think creatively, so one can actually integrate these hygroscopic materials with this hydrophilicity switchable polymers at a molecular level. So this is the idea, the water release process actually can be achieved instead of conventional way. So you have this liquid-liquid phase separation process to reduce the energy needed. And this actually can be serving as hydrophilic polymers, serving as water reservoir, and it can be controllably switched to the hydrophobic state at a mild temperature and release the water without the energy intensive process. So if you think about what materials you can use, so the IPN, interpenetrating polymer network, is this new class of promising materials that you can actually combine these two networks with different functions. So for example, one network for hygroscopic to take the water from the air, and the second is actually for the hydrophilicity switchable. So to switch the state from hydrophilic to hydrophobic and then to release water without this energy intensive process. And then so this slide really shows our molecular design that published last year. So this design composed of hygroscopic polypyrrole. So this is hygroscopic materials and then penetrating into this thermal-responsive polynipan material. So this synergistic effect can actually happen with this molecular level integration of this hygroscopic with these thermal-responsive gels. And this is also shows, SEM shows the polyp structures for this hybrid hydrogels with IPN networks. So this slide quickly show you some of this comparison. If you look at the SMAG materials, combining these two polypyrrole chloride and the Nipan, so you can see at various relative humidity, so they can take in water efficiently. So for relative humidity 90%, they can take up to about 7 grams per gram of your dry materials. And this is like a photograph shows you the dry state versus your swollen state. But if you compare it to the polypyrrole chloride, one of component only, so this molecular dynamic simulation shows this water clustered in these pyrrole centers, and this experimental and simulation data shows they have limited water uptake. And also another component, polynipan, if work alone, so they are good water absorbent, liquid water, but they are not good moisture harvesting at the relative humidity even 90, so barely can absorb the kind of water vapor. So you can really see that the SMAG is the high performance of moisture capturing of SMAG is coming from the synergistic effect of hygroscopic and hydrophilic. So basically, this water can quickly liquefy on the surface of SMAG and then transfer to this molecular transfer to the Nipan as water reservoir, and then swollen to take more water in. And if you look at another key feature for this design is water release step. So this is actually one picture one scheme shows you that we found these two modes during the water release. So for the high water uptake, there's this express mode initially. So this means that the gel, when heated up, mildly heat up to about 40 degrees C. So this is their lower critical solution temperature. So they can switch from hydrophilic, water-like, to the water-dislike, hydrophobic, and release water efficiently. And then as you move on further, so they can still have this normal mode using this evaporation and condensation. So you can see this is where for high water uptake, you can really take advantage of the express mode. So this is really coming from this molecular configuration change for your Nipens that is at a temperature around your lower critical solution temperature. And then given this efficient water capturing and then water release, so we designed these 24 hours multi-cycle water release and water capture and release at a relative humidity of 90 and 60. So you can see the optimized condition is 1 hour as a one cycle, 50 minutes for absorption and capturing, and then 10 minutes for release. So each cycle is going on, so you have 24 cycles a day. So basically you can release about 20 or about 50, even liter of the water per kilogram for your material use. And this photograph shows how much water they can actually take in and swallow. And we also shows these outdoor water harvesting behavior studies under natural environment. So you can see we use this mesh bags design. So in the dry states, these zero gels, and once swallowing at hydrogel at these early morning hours, so they can take in the water significantly. And then once it's subjected to the solar heat, so over the time, so they can release water and efficiently. So this really shows you this new design of hygroscopic plus the thermal responsive polymer, so can actually do a good job in both process. So I already summarized some of these exciting developments for on the materials innovation for atmosphere water harvesting technology. And I think it's very important to re-emphasize the design principle for the next generation materials. So they need to have this strong interaction with water to enable operation at a lower, even lower relative humidity or high temperature conditions. And then you also want to design a dedicated design of molecular level water management to realize that water will release efficiently. And for long-term operation, both the chemical and the structural stability are quite important. And for better, higher flux airflow passing through the solvent for better yield. So you can also optimize micro or nanostructure of your gel materials. And you can also you need to design faster absorption desorption kinetics to achieve the higher production capacity. And so we recently wrote a mini review for this field. So if you are interested, please read our reference, just come out actually early this week. Thank you. So let me stop sharing and then turn to the next speaker.
Thank you, Guihua. Okay. Thank you for sharing the insight into this technology, particularly from materials point of view. Okay. So next speaker, we have Professor Peng Wang from Hong Kong and the Coast both. Okay. Peng, that's your turn. Okay. Go ahead. Peng, please share your slide. Professor Wang Peng, please share your screen. Okay.
Can you see mine?
Yes, that's okay now, please.
Okay. All right. Thank you, TJ. So after Guihua's talk on material innovation, my part will be on practical side. In this part of my talk, I will share with you or show some of our all-in-one, easy to assemble device. I'll show you some of the nano design we designed to enhance the absorption-desorption kinetics, and also application of AWH to PV panel cooling. To start, I still have to introduce you one material, one solvent material, which my research has used a lot as a reference benchmark. I believe Guihua actually briefly touched upon this material in one of his slides. Now the material here is composite hydrogel of PAM, calcium chloride, and the carbon nanotube. And you can see from this figure, it has good cyclability, but a very slow absorption desorption kinetics. It takes this material 14 hours to reach its vapor absorption equilibrium. Nevertheless, we put this material inside a very easy to assemble, inexpensive all-in-one device, and you can see on the bottom right, due to the slow absorption kinetics of the solvent, this device only allow us to do one cycle of absorption and desorption within 1 day. With that, 1 kg of the solvent would give us only 1 liter of fresh water within 1 day period. Now, in order to have multiple absorption desorption cycle, kinetics has to be further enhanced. One of our design is to have desiccant in nano container. The example here is that we have lithium chloride as desiccant, and we have nano hollow carbon sphere as our nano container. Now with this material, you can see on the left-hand side, this video shows that upon illumination, there is very quick release of water vapor, indicating that the solvent material has a very fast water vapor desorption kinetics. It takes this material now only 3 hours to reach its vapor sorption equilibrium in comparison to 14 hours in the previous case. We then put this material into another down-to-earth, very simple to assemble device and to test its performance. Now with this system, we were able to do 3 sorption-desorption cycles within 1 day. With this, we were able to get 3 kg of fresh water out of 1 kg of the solvent material. Well, since we have been this far of having multiple cycles within 1 day, why not 1 step further? So we are currently working on a continuous AWH device and showing in this video here. For the sake of time, I'll skip the detail, just let you know this is work in early progress. I hope I will have some update to share with you soon. Now I want to very quickly switch gear to something everyone knows very well, PV panels. The global PV installation capacity is currently at around 600 gigawatts, and it's on a very fast rise. The reason I talk about this is because PV has a serious problem. It's very hot, especially in arid and semi-arid region during daytime. So in one of our projects, we combine AWH with PV panel to offer some cooling power from the AWH design. Now, the design is presented here. Basically, we have AWH sorbent that sorbs water vapor at night. During daytime, when the PV panel is heated up, the heat of the PV panel will be used to drive water to evaporate out of the solvent material here. That leads to effective PV panel cooling. To test this design, we use again the same composite hydrogel material we worked before. And you can see from these 2 figures on the right-hand side, with the AWH assisted cooling, you have the same PV panel had much lower temperature than the one without. And in our field outdoor test, the same PV panel with the cooling design was able to produce 13 to 19% more electricity than those without this cooling design. So this is all I have. To end my part, I really want to echo the message Jean conveyed to all of us in the very beginning. There are currently about 8 million people in the world who just don't have daily access to clean drinking water. Now, this leads to, very sadly, about 200 million hours, human hours, spent majorly by women and girls just to fetch water for their family. If and when we make AWH able to give them the amount of water they fetch every day, this amount of human hour will be saved. And this time can be spent on much more productive activities, education, skill training, manufacturing, you name it. So this is one motivation that everyone should work hard, should continue our work on this topic, and everyone in the audience, if you are interested, should join this great effort. With that, I would like to thank you for your time and your attention. I'll pass the mic to another Professor Wang.
Thank you, Peng. Yeah, thank you for sharing those very exciting devices. Now we would like to invite Professor Wang Ruzhu to show the progress at the system and process level. Thank you. Professor Ruzhu, please share your slides. Go ahead. Yeah.
Start from the beginning. I'm sorry. Just a moment. I need to. So thanks for the invitation from Professor Wang from MIT to give me this opportunity to talk something about extracting water from air. And my topic will be energy, water, air, and nexus. So fresh water scarcity, that's a global challenge. And you could see that many people in sub-Sahara desert area that take hours to collect drink water every day. So there are so many people, there are lack of fresh water, but water is everywhere, especially in air. So here we could show that there is over 6 times of the amount of water in the liver actually on the earth. So it's actually now in the air. So we need some technology to try to get water condensed, and then we get condensed water for drink. So now there is some machines available. This is one example that to take water from the air and you get potable drink water, or some kind of facilities in the desert area to fetch water from the air. So water in air. So 1 cubic meters, how many gram water in air? That's only 25 grams. So if we want to collect the 1 kilogram water, so you may handling about 80 to 500 cubic meters air. So this is based upon have a 50% uptake efficiency. So in this case, you need consume energy. And currently, if we have a look, so there are several types of air water harvesting technology. The most popular is a dew water collection by refrigeration effect. But also now we are talking about absorption based. So this is depending on the relative humidity. When relative humidity is 100%, you could use this kind of fog fix. But when the humidity is very low, only the absorption based is a solution. So this just to show that if we have the air, 20 degrees, 65% relative humidity. So with the humidity, 9.5 grams. So then if you wanted to get 5 grams down and you need cooling to the dew point, and then cooling down again, and in this case, the temperature will be about 2.3 degrees centigrade. And you need the cooling source, maybe minus 2.6 or even lower to get this condensing. And in this case, you consume the energy. So you need to consume electricity. But if we have adsorbent, when it's adsorbent, we just try to heat up. And then when you heat it, the water adsorbed will be generated at a high pressure in this case. And then you find the dew point will be high. For example, here, that's 32 or 34 degrees centigrade. And so in this case, if we go through this process, and you need about 30 degrees here, and in this case, because the heat sink is about 20 degrees, so you have 10 degrees temperature difference. So in this case, we need some generation temperature, maybe 10 degrees higher, for example, 50 degrees. So in this case, it's possible that you get condensing at the heat sink of the room temperature. So we made an evaluation, maybe the humidity of air, 10 grams, could be the critical point for the selection of dew condensation or absorption. So if it's higher than 10 grams, maybe vapor compilation system is very efficient. But when it's lower than that, the absorption system should be used. So the humidity of air at the water deficient regions are low. So in this case, we need to consider the absorption-based AWH systems for the humidity below 10 grams per kilogram air. And we made an investigation, typically in Egypt, Iran, and Australia, and China, some delta area. And we find during the night, normally the humidity so increased and the temperature is down. But in some island conditions, so the humidity is high. So in this case, for the dry area, absorption-based is a good technology. So Professor Guihua and also Professor Peng Wang had already a lot of discussion for the solvent design and to realize highly efficient AWH. So I just try to escape to use morph materials or some hygroscopical hydrogels or some thermal responsible composite hydrogels. That's all so reported by the two professors before. And also hygroscopic azide confined into some porous matrix to use some calcium chloride or lithium chloride and combine it together with some porous materials. And there are already some models to show some discontinuous working devices to capture water at night and release water at the daytime by sunshine. So this is reported by MIT and COST and also some other facilities. So, and by Professor Yagi, for example, also. So there are many these kind of researchers. But in consideration, if from materials to commercial systems, we have some programs. The first is scale up absorbent. So normally for some taste of materials, you only taste several grams, but you need kilogram or larger scale. And also you need the low cost and to get a stable materials. And also for the system level, you need to scale up these devices from very small quantity, less than 1 liter, you need 10 liter or 500 liters or more. So in this case, you need to consider the heat and mass transfer of the design. Also, the cost is very important. A lot of morph materials, and then we estimate from the low materials, and we found the solvent could be very expensive. But if you use the normal silica gel or zeolite, and so they are very cheap. So in this case, how to reduce the cost of the solvent. And also, if you get the material optimized, you need the system optimization to get a solar water heating powered AWH. So it's by solar energy. So the system design, you need a very good heat and mass transfer. And also the waste heat should be recovered. In this case, to get a high efficient AWH system, or even to use a solar PV driven system for the combined with a heat pump to get a more high efficient. So in Shanghai Jiao University, we had a demonstration for 50 liters per day AWH system just from one cycle. And during the night, we get the air, so adsorption, actually moisture stored in the adsorbent bed. And during the day, it's heated by the solar energy, and then close these two valves and then make the circulation, and then you get air heated, and then you get a high humidity air, and then condensed liquid in the condenser, and then you receive the water collected. So this is a full system of 50 liters capacity. Actually, we did some tester. We use ACF combined together with lithium chloride. So it's try to use a commercial available adsorbent, and it's a mixture of liquid and a solid. And this is testing that at a different temperature levels and for the adsorption that changes with relative humidity. And then we build this system, it's running, and we take a solvent about 70 kilograms. So one day, so we take 3 conditions. And the student is very inspired when this kind of running, and she said, my mommy actually, so it's for the, she is very inspired for the achievement. So then we did some test, typical conditions for this kind of facility. And also we made some evaluations. So this is a real test for the run, and the energy evaluation is nearly 2.3 kilowatt hour per liter of water. So we made an evaluation for the vapor completion due water collection. That's electrical consumption. So it seems that it's reasonable to make completions with a vapor completion system for due water collection. So besides AWH, I take very quickly to say something energy, water, and air nexus. So we did some researches of electronic cooling by AWH by absorbing water to the morph materials. But for the electronic heating, we heat it. So without heating, without morph material and with morph material, due to the desorption, you get a temperature down 7 or 8 degrees for the electronic cooling. We invented also air humidity pump to pump water humidity from low environment humidity to high humidity. And also we tried to use wind solar radiation for the heating and by photothermal effect to generate evaporation and then to create concentration granite around this panel. And then indoor side to absorb moisture. In this case, you get dehumidification of the indoor. And also we create so-called thermal battery by air humidity assisted absorption. So by this kind of absorption of air humidity, you get absorption, you get air heated. In this case, this could be used for heating, but in the night, you could use electricity for the regeneration. So in this case, this is a kind of new high density thermal storage devices, but you need to keep the output of temperature, and so power could be controlled in several hours you need. And also, we did some work to consider sustainable agriculture for water-saving greenhouses. So we try to absorb water during the winter times, and then by absorption heat for heating, but the water collected could be used for the irrigation of this kind of plant. So in this case, we could get water recovery more than 70% and to get energy saving and water saving. So this is a new research for the agriculture. And also we have a desire, data the brooms with drought planting, use hydrogels like this. So we do not want to use this. And we would like to use polymers, peanut palm. And in this case, actually, the plant actually will just go through the connections and not free water, but what contained the polymers. So in this case, to save the water for this kind of agriculture. And also the last slide just to show we invented the next generation room air conditioner with desiccant heat exchangers. So this is a design, and we increased the normal room air conditioner COP from 3.2 to 6.2 because 40% cooling load for dehumidification is handled by desiccant. And this desiccant actually that's generated by the waste heat from condensing heat. So in this case, we enlarge COP. Fortunately, now we had a contract with a train vehicle air conditioner manufacturer. We try to use this for the train vehicles, not only for the metro, but also for super high-speed train. So we hope in the next year we could test this kind of system. Now it's already sent into the testing of the laboratory. So the outlook and perspective for AWH, I think we need the solvent design, device construction, system optimization, and also cost reduction. But also beyond AWH, we need also some more could be expected based on innovations. So that's all for my talk. So this is all the student that's involved, and we call it ITWA. That's an innovative team on energy, water, and air. So thank you very much.
Thank you, Ruzhu. Okay, I think it's a very exciting talk and put a lot of aspects together in an integrated way. So, and also we can look forward to the future. Thank you all for the presentations and also for the participants. I think this year, unfortunately, we had the COVID-19 pandemic. So it really changed our life. And even for myself, I was thinking about why before we take everything for granted, like food, right, water, energy, everything like for free. So right, it's like everything is at hand. Now, like water is now clean water, particularly not for United States, maybe for other countries like me, I'm in the Middle East. It's difficult to get clean water, right? And with a very low cost. And also many things we should think about decentralized water production. One of the most exciting technologies is from atmosphere we can harvest water, right? So many issues I think we should discuss through this panel discussion. And before that, I would like to also launch another poll, because as Professor Peng Wang mentioned, there are many other technologies are available for standalone operation. So I would like to launch another poll just to get an interaction from our team. Okay, so let me just launch that again. Okay. So the second poll is basically, so which of the following water production technology sounds more promising for people live on off-the-grid island, people like me, okay? So first one is PV powered reverse osmosis membrane. Second one is a solar thermal distillation, like recently people developed direct solar vapor generation technology. And also the last one is atmospheric water harvesting. So just put your guess over there. There is no open solution for this, okay? We just think about predict the future based on your own kind of experience, okay? So the poll is coming, okay? We have more than 40% votes, good. Wow, many people are convinced atmospheric water harvesting is most promising. Wow, we did a great job today. Okay. Okay, very good, very interesting. Okay. Okay, sounds okay, good. So not too many people vote PV, okay? Is that because PV cannot work during night? Maybe that is the reason, right? Okay. Sounds good. We have more than 70% votes already. So now let me just end the poll right now. Let's do it for 75%. Just request all the participants submit your votes as soon as possible. Okay. So just give a few seconds. Okay. So I think it's almost there. Okay. Sure. Good. Yeah. Let's good. Let's end the polling. So now let me read the results. Okay. 23% of people vote PV powered reverse osmosis membrane. Okay, is more interesting, more promising. And 24%, okay, slightly larger than the first one, is vote for solar thermal distillation. And the last one, more people, more than 50% of people voted atmospheric water harvesting. So Jean, are you happy with this poll? Okay, I think definitely all three other speakers are very happy because we promoted technology very well today. Okay, very good. Okay, thank you. Maybe you can, we got multiple questions from the participants. I think let's have some interaction section. I marked a few questions here. So the first question I'm going to read is, so silica gel usually needs around 1 kilowatt hour for dissolving 1 kg of water. By how much is the desorption energy reduced in IPN hydrogel composites compared to silica gel? Who is going to answer the question? Definitely from technical side.
So maybe I can add some thoughts. So like a silica gel is this conventional moisture harvester. So they typically need to have these high energy and to reach regeneration temperature, and then the adsorption enthalpy to overcome. I think compared to IPM, which is actually going through liquid-liquid phase separation. So we did not do a calculation and comparison accurately, but these the enthalpy involved a change for the phase this liquid-liquid thermal responsive hydrogel to change from hydrophilic to hydrophobic is about 1 or 2 orders lower than this conventional evaporation condensation for the desorption process. So that actually really makes the process less energy intense. So I think that's my input.
Great, thank you. Another question from Mike Lezenson. Okay, so the question is, how resistant to microbial growth are the water harvesting material? And also for some other question, I'm talking about contaminants and in the water. So maybe Jean, you want to address this briefly, and all other speakers.
Yeah,
Clean
it sounds
water.
like it sounds like a technical question in terms of the separation of the technology from microorganisms.
Yeah. Okay. So from technical side, Peng Wang, maybe you can address this.
So I feel most of the material that we have been working on are microbial activity resistant, either polymers or the liquid salt, or some other solid material, silicon gel. So the second part is on the, can you repeat the second part on the?
Contaminates from water.
Well, if you only talk about the air pollutant, I would typically say that the water should be less when you compare to fog harvesting. Why is this? So the reason I believe is that firstly, the contaminant concentration in air should be much lower, because we are in this case talk about molecular level contaminant as gas molecule in the air. So there may be so far we haven't, or nobody else have done long-term performance evaluation. There may be potential microbial contamination within the produced water by solvent-based water harvesting. But so far I haven't seen, or at least we haven't done any long-term experiment to evaluate this.
Okay, thank you. Yeah, so there is another question from Xianming Dai, okay, to Guihua Yu. So very interesting temperature response material for water extraction. And where is the energy from for heating and cooling in your device? If we use a portable device, what would be a good source to get the energy? For the Guihua, this question for Guihua, go ahead.
Yeah, so in the demo for indoor and also outdoor using our SMAC super moisture absorbing gels. So basically the idea we want to promote is, because the thermal responsivity of this gel, it's only required like mild heat. So the heat can come in from the solar heating, mild solar heating. So once the temperature reach to about kind of these LCST around 37 to 40 degrees C, so they can switch it from hydrophilic to hydrophobic to release the water. So that solar can be one source for energy needed. And also if you have any of electricity involved, so the hot plate heating in the lab is also more than efficient to release the water. And for portable device, I think it is really needed for kind of take advantage of a solar power design. So that's the whole, I think, the perspective Professor Ruzhu Wang promoted, using the solar-powered AWH has the greater kind of promise compared to PV and compared to other electricity involved process.
Maybe Professor Ruzhu Wang, you can also comment on this since you have been working in the field for a few decades now. Yeah.
So I think the most important thing for the energy consumption. So I think as Guihua introduced that using these kind of temperature responsive materials, normally because adsorbent we need the generation temperature. Maybe you need 60 or 70 degrees centigrade, but for this kind of hydrogel, he need only 40 something. So in this case, so the energy consumption could be very small. So I really wondered that the invention of Guihua, actually it will be very, very efficient, because for the adsorption AWH systems, now what I considered that to compare with vapor compression system, I made some calculations, maybe say 10 grams per cubic meters for the air, this kind of dryness, maybe below that it is suitable for adsorption system. But if we use this kind of hydrogel, the temperature responsive hydrogel, then the energy consumption could be much lower. I think it's a very good basis, and to use the solar energy, then very, very easy.
Thank you. Thank you both. Another question from Yusuf Wahabi. So the question is for Professor Peng Wang. So the question is, radiative fog is very common over Arabian Peninsula, especially around the winter time with high near surface relative humidity. How does your absorption-based design work during fog conditions? Professor Peng Wang, since you have been working in the Saudi for a long time.
Well, that's a very good question. Unexpected. I have been. This is true. I have been in Saudi Arabia for the past 10 years. Well, I remember there, in the place where I work, there was only a couple of days of very heavy fog in the past 10 years. Regarding how this material work during foggy day, if you talk about hydrogel, or you talk about some solid based solvent, they will be saturated with the liquid fog droplet very quickly. And the rest of the process will be the same as the vapor-based water absorption and desorption. You have to have the energy to drive the water out. In our case, it's A involved the phase change. Then there will be significant amount incoming energy to drive the whole phase change process to release the vapor back, and then condense the vapor to get the liquid water.
Okay, great. So now I have another interesting question. Okay, the question is the use of AWH on planets other than Earth being investigated? So basically, are we considering using technology on, let's say, Mars, Moon, since they have water over there underneath, right? So, Jean, maybe you can put some perspective here.
I can't imagine on another planet what's going on. I think that just to come back again to one of the most unique things about atmospheric water harvesting is being able to produce the water where you need it. And if we can get the volumes up, I think one of the unfortunate use of terms in defining the Sustainable Development Goal has been calling it drinking water. And it really should be called domestic use water. Because I've noticed in many literature on atmospheric water harvesting, engineers are thinking about how many glasses of drinking water can their technology produce. And what we really need to be talking about is how many liters of water can be produced at the place where it's needed, whether it's in a mud hut in Africa, or whether it's in a station on Mars, because most of the water that's needed is actually not for drinking, but for hygiene. And that water is what is really right now causing us to lose so many IQ points in human populations.
I see. Okay. Then now we also need the opinion, right? The recommendation from our engineers. So how about other speakers? You can comment on this.
I agree with what Jean just said. However, one of the signature of AWH is that it produces very clean water. If you do the whole process right, the water produced by this process is typically much cleaner than drinking water produced by conventional procedures, either for mostly for the centralized drinking water treatment. So if we can think about where do we put this precious clean water into a good use, drinking is of course our first priority. Drinking, cooking, those are the activities that make you survive. There is 3 liters of minimum drinking water demand for a typical adult. If we, first to have the AWH to meet this basic essential need for everybody, then we can move on to push this water to other use. I'm not expert on personal hygiene, but maybe I put this on the my second priority list. It's just my personal take on this. It's very clean water. That's a fact.
Mm-hmm. Okay.
It definitely is. I think just not to lose sight of the need for volume in terms of maintaining IQ, in terms of maintaining brain function of young children, and so once the first need is met for drinking and cooking, then other uses are deprioritized by families. Mothers, if they have to walk a long way to get water, they'll drink and cook with what they get, and hygiene will be deprioritized. And that's right now where we're losing human capital. So it's just to keep that to keep that in your thinking of yes, quality is super important. Quantity is also very important.
Right. Thank you.
Okay, great. Let's take another question. This is from David Wasinger. So a question for the panelists, all the panelists, okay? So what are the cost figures today for each of the leading water vapor harvesting technology? For example, in dollar per liter, okay? And also where do you see each of the most compelling ones going in the next 10 years? So this is like a practical, I think, question. Okay, and a comment from panelists?
What I have read from some literature for vapor compilation system for the dew collection. So they reported that its energy consumption is somehow between 1 to 6 kilowatt hour per liter of water. So this is actually the cost of energy actually. So not including the equipment. But usually this equipment is a long life for the devices. But for the sorption-based technology, so to produce 1 liter, so if it's not by Guihua's and what our facility did, you need 1 liter, you need about 2 kilowatt hour heating. So it's not that much, but it's less than electricity price. And if Guihua's material is used, you could reduce a lot. I think this is actually relative with the cost. But I think Wang, he had already listed his cost.
Well, it was a very rough estimation. I have to emphasize that for our cost estimation in one of the slides, because you guys saw the material we use, you know, lunch box, glass, aluminum foil, copper foil. Those are typical supermarket material, and we consider the cost of the chemicals that we use to make the hydrogel. What we did not consider was we don't have a very reliable data on how long those hydrogel will stay stable, because it is known that all of the polymers will gradually degrade under solar irradiation. You know, this is like the context of our rough cost estimation. I want to say that the system can be very simple, easy to assemble, easy to maintain. So it's suitable if you have available land. It's suitable at small to medium scale. You know, a household to a small community with, you know, few hundred people. And if you do the operation, if we can first, you know, if we can scale up fantastic materials at large scale with reasonable cost, it's reliable, you know, and there's no consumable typically during this whole process. So as long as you make the system or the material stable for a long period of time, the cost can be reduced significantly. That's my personal opinion on this.
Yeah, so maybe I think just add very quick points to Peng and Ruzhu's comments on the cost. I think it's very important questions to look at further in terms of from what we can do as scientists and engineers to estimate the material cost, but for the system level, how you build a system with different components and how long it can work. So it's really kind of a next step we need to look into, and also for all of these groups working on this field to think about is how competitive with rows and numbers from the industry. I think it is extremely important question to look into. Yeah.
Thank you all. Let's take another question, last one, okay? So this is from Pablo L. So the question is, could it become dangerous for biological processes if we extract too much water from air? so this is a controversial question. Okay, go ahead. Yeah, from our speakers, any comment on this? Do you think we can extract too much water from air?
Yeah,
I wish so.
If we, you know, we successfully scale up this whole process, it will be, I feel it will be contribution to climate change, because we are getting water back to, you know, from air to the ground.
Mm-hmm.
I don't think we can, you know, with the human activity at current stage, you know, if we scale this up at the scale we need, the amount of water coming down from air is still very, very small compared to what we have in, you know, in the atmosphere.
Okay, good. So since time is very limited now, let me just thank you very much all the panelists. Okay, so I think this is a great session today, and also thank you all for the contribution. So I just want to mention a few things here. So we next seminar is will be held on July 22nd. The topic will be high thermal conductivity materials. So we're going to have another 4 speakers plus 1 panelist. Okay, moderator. Okay, that's one announcement. So also want to remind all the participants. So in the future, we'll have multiple events On August 5th, we have a hydrogen energy, and also August 19th on thermal management of electrical vehicles, and also September 2nd. We are going to have another kind of seminar on Earth energy balance. That will be very exciting to me also. Okay, so that's all for today. So we are just on time. So if not, if you don't have other questions, let's just finish today's curriculum. Okay, thank you very much. Thank you all
Thank you.
for today. Okay,
Thank you.
Thank you.
thank you.
Bye-bye.
Bye.
Bye.